Hi everyone, today I'll be talking to you about the eigenvalues of graphs, and to me this is an insanely cool topic. It's got some beautiful theory, it's got some amazing applications in the natural sciences and in the social sciences, and we're going to talk about all of that, but we have to start by clarifying some basic definitions. So if you've taken a class in linear algebra, you already know what eigenvectors and eigenvalues are, but in case you haven't, I'll take some time to briefly explain what they are. So in the picture below, we have a vector x, and x is being pre-multiplied by a matrix A, which I haven't shown here, and what you get is a scaled up version of the vector x, so essentially x times some scalar. So what's going on is that x is a particular kind of vector called an eigenvector. And an eigenvector is essentially a vector that, well, if you pre-multiplied by matrix A, then it simply gets scaled up by some scalar through the linear transformation A. And that factor by which it scales up is called the eigenvalue. So just to repeat an important point, eigenvalues are the scalar factors by which linear transformations scale eigenvectors up or down. So if you have multiple eigenvectors in the system, you will have multiple eigenvalues scaling them up or down. And in the examples that we'll look at, we will have multiple eigenvectors, and so we'll have different eigenvalues that we're looking at. Now, having discussed some of the definitions and preliminary ideas related to the theory of graph eigenvalues, let's start actually talking about why graph eigenvalues are actually interesting to us. So, if you'll recall, right near the beginning of the term, we discussed some matrices related to graphs. Most notably, we studied the adjacency matrix. And here in this image below, you can see a graph, and its adjacency matrix is kind of shown on the right. Now, the interesting thing is that adjacency matrices, by definition, are square matrices. And so they're linear transformations, and you can find eigenvalues for them. So essentially, what's going on is that you take a geometric or graphical representation of a graph, like the thing you have on the left, and you create a numerical representation of it in a matrix, like you see in the adjacency matrix on the right. And when you find the eigenvalues of the adjacency matrix, you're essentially finding a quantitative you're finding a quantitative value related to the graph, which can give you interesting information about qualitative aspects of the graph, for example, its chromatic number and its diameter. And the interesting thing is that you don't even need to look at the actual structure of the graph even once to do this. You can just find its adjacency matrix, you can put it into a computer and find its eigenvalues, and you immediately know about some qualitative aspects. And that's the interesting thing about the theory, and that's what we'll learn about just now. So here's the first interesting theoretical result from the theory of graph eigenvalues. It's a theorem that says that the diameter of a graph G is less than the number of distinct eigenvalues of G. So I've taken this example from a paper that I used to study for this topic, and we'll use this example to actually understand this theorem. So we have this graph G on the left, we have its adjacency matrix on the right, and I kind of put the adjacency matrix into a calculator and I found the eigenvalues for it. And so the eigenvalues we found are 3.37, minus 2.37, minus 1, minus 1, 0, and 1. And so the number of eigenvalues is 6, but as you can see, the number of distinct eigenvalues is only 5. And so the diameter of the graph G is less than 5. And you can kind of see that on the graph on the left by yourself. It really does look like there's no path greater than length 5 on the left. And so from this really cool theorem, we know that since there's 5 distinct eigenvalues, the diameter cannot be greater than 4. Another interesting theoretical result is the idea that if you know the eigenvalues of a graph, then you know something about its chromatic number. In particular, the chromatic number of a graph G is at most the largest eigenvalue of G plus 1. So, for example, in this example that I've been working through, the largest eigenvalue of the graph is 3.37. So 3.37 plus 1 is 4.37. And so From this theorem, we already know that the chromatic number is at most 4. At least to me, this is really fascinating because we have a quantitative value associated with the graph, namely its highest eigenvalue, and we don't even need to look at the graph, and just from this quantitative value we know something qualitative about it, namely its chromatic number. And so at least that's very fascinating to me. The next interesting theoretical result has to do with decomposing the graph G with some bicliques. And remember, biclique is a complete bipartite graph. So the question is, how many bicliques do you need to decompose the graph G? Now the interesting thing is that if you know something about the eigenvalues of G, you can answer this question very quickly. And the theorem says that the minimum number of bicliques needed to decompose G is the maximum of either the number of positive eigenvalues or the number of negative eigenvalues. So for example, in this example that I've been working through here on the left, we have 3 negative eigenvalues and 2 positive eigenvalues. So the maximum of 3 and 2 is 3. So we know that we need at least 3 bicliques to decompose G. And just like the previous result, here's a case where just from knowing the eigenvalues, you know something qualitative about the graph, namely the number of bicliques needed to decompose it, without even looking at the graph. With just the adjacency matrix and the eigenvalues, you can find something qualitative about it. And again, to me, that's very cool. One final result that I wish to talk about was, to me at least, a very beautiful result, and it has to do with regular graphs. So it says that a graph is connected and regular if and only if the matrix with only ones as all of its entries is a linear combination of the powers of the adjacency matrix. So this doesn't necessarily have to do with the eigenvalues of G, but it was related to the research I was doing for this. So for example, in this example that I've solved through below, we have a regular graph and we have its adjacency matrix. So if that adjacency matrix, if you can take its powers and you can sort of sum them together in some way to get a graph which just has like all ones as entries, then we know that the graph is both connected and regular. At least to me, that was a very cool result. So having discussed some of the interesting theoretical ideas from the field of graph eigenvalues, let's talk about some of the interesting applications of it. So before I go into some applications in the natural sciences, I just want to mention some mathematical applications of it which were relevant to this class. So as you can see on this slide, we see like a number of objects, or a number of mathematical objects, such as digraphs, spanning trees, Hamiltonian sets, k-colorings that we looked at in this class. And the interesting thing is that graph eigenvalues help us create efficient algorithms to count all of these things. And so the methods that we used in our homeworks to count, for example, the spanning trees of a graph or Hamiltonian sets of a graph, we can create much faster and more efficient methods for them using the theory of graph eigenvalues. One of the most interesting applications of graph eigenvalues is in the field of quantum chemistry. So before I go on to the interesting result on this slide, I need to explain what an unsaturated hydrocarbon molecule is. So in organic chemistry, if you have a molecule with just carbons and hydrogens, and like you see some double bond, like for example, you see the 2 lines between the carbon atoms here, the C and the C, that's a double bond. So whenever there's a double bond, that means that there's like some hydrogens that like the carbon atom cannot connect to. So that's what the unsaturated and unsaturated hydrocarbon means. So yeah, that's like a preliminary definition we need to know, but let's get to the interesting idea. The interesting idea is that if you have an unsaturated hydrocarbon like this one, you can represent it as a graph. So this is going to be like a non-simple graph with each of the atoms, the C's and the H's, represented with vertices. And for example, between the 2 C's, there's going to be 2 edges, and between the C's and the H's, there's going to be 1 edge each. So yeah, let's say that you take like that molecule and you represent it with a graph G, and you find the adjacency matrix of that graph G, and you find its eigenvalues. The interesting thing is that when you find the eigenvalues of the graph, they correspond exactly with the energy level of the electrons of the molecule G. And, well, this is really very fascinating because suddenly we have this very theoretical, very quantitative concept, namely the eigenvalues, and it corresponds exactly with something we find in nature, namely the electron energy levels in this graph. So that's very interesting. So another interesting application of graph eigenvalues is in the field of epidemiology. So you can use a dynamic graph G to model the spread of an infection over a map. And there is something called the epidemic threshold of G, which is essentially the state of this graph beyond which the infection becomes endemic. So you can think of it as a kind of tipping point of the graph. Like once you reach it and the infection kind of goes beyond it, the infection becomes endemic. And what that means is that it starts to occur in the population at a certain baseline amount, and it can never kind of go below that baseline amount. So in a very interesting paper in 2003, some researchers, Yong et al., showed that this epidemic threshold has something to do with the graph eigenvalues of the dynamic graph G, which was used to model the infection. So if you find the graph eigenvalues of G, then you can predict the epidemic threshold. And in particular, I think the epidemic threshold is less than the maximum eigenvalue of the graph. So in this presentation, we talked about what graph eigenvalues are, and we saw some interesting results from the theory of graph eigenvalues, and also some very cool applications of graph eigenvalues. So I think that we talk a lot about the utility of mathematical theories when it comes to justifying why exactly we do mathematics. But I think that an equally, I guess, valid motivator for doing mathematics is just like the aesthetic beauty of the theories that we work with. And at least for me, this particular research project constituted working with a particularly beautiful set of mathematical theories. And I guess the reason for that was because in my own head, and in the way I intuit things, linear algebra is very much a numerical part of mathematics, which kind of has more to do with computation. And graph theory is more of like a geometrical aspect of mathematics, where like shapes of graphs and like the way that they look qualitatively, that matters a lot. And so I kept saying throughout the presentation that it's kind of surprising to me that you can take a quantitative variable from a graph, like for example its eigenvalue, and you can predict qualitative things about it, which it's really very fascinating. It really shows the degree to which you can take qualitative data from a graph and you can kind of compress it into a matrix and compress it even further into eigenvalues. So in that sense, it's quite beautiful. But I think it's beautiful even in like sort of a higher sense, where it's like you have these two different fields of mathematics. You have linear algebra and you have graph theory, and they're kind of synthesized in a very fascinating way. It's almost as if when you find the adjacency matrix of a graph and then you kind of do some mathematics with it, it's almost as if you're mapping the graph into a completely different field of mathematics. It's almost as if you're using linear algebra as a map for graph theory, and you're just kind of doing your math there. And so at least to me, it's kind of beautiful that you could do that. It would probably be pretty fascinating if you could do this with like other fields of mathematics too, where you could just take, for example, I don't know, like set theory or something, and then you could just sort of find some parallel between set theory and graph theory, and you could work in set theory and find results in graph theory. That would just, it's so aesthetically beautiful, and it's extremely fascinating when you can do that. So for that reason, like, this research was a source of real wonder for me. At least to me, I thought it was beautiful. So anyway, that's just some discussion that I added at the end, and here are the sources that I used to make this presentation, and thank you very much for listening.